This is Lab 23 on Kernel PCA, following Lecture 23 on Kernel PCA. So today we want to talk about Kernel PCA, and the library for doing Kernel PCA is called Kernel Lab, and you may need to install that. But we can load up that library, and the function for running Kernel PCA is called kpca. So here we can learn about our Kernel PCA, and they even call it a nonlinear form of PCA. And so you pass into it your data. Typically, I guess you can pass in just the kernel matrix, which we know from lecture you can pass it in. You tell it what kind of kernel. So RBF dot is the Gaussian kernel. Poly dot is that polynomial kernel. You can work with the linear kernel. There are all sorts of other kernels you can work with, and you can read up on these. And they are all implicitly defining some kind of embedding in a higher dimensional space. But as you see, you only actually specify what the kernel function is. There are, depending on the kernel, there are various hyperparameters. So like sigma here is basically our, they say, inverse kernel width. So it's like precision, or it's like 1 over variance, something like that. Then for, say, polynomial, you can specify the degree, you can specify some scale and offsets for various other of these. And you can read up on those. And the features, I believe, features here is going to be how many components we want to retain when we do our kernel PCA. So that would be like Q in our lecture, or it would be the number of columns, but it's the dimensionality of that lower dimensional space that we return. So there's other stuff. You can look at it. It gives you back what's called rotated, which is basically the projected down data, which is the original data projected on the PCs. So it's theoretically, although you don't actually have to work in that higher dimensional space, it's embedded up in the higher dimensional space and then projected down to a subspace, and we get the projection of the data onto the subspace, onto that finite dimensional subspace of that potentially infinite dimensional space. And you can actually get the loadings or the weight matrix for that, which is going to be basically the U matrix from the SVD or the corresponding eigenvalues. So to build up an example, I think a nice example would be to go back to kind of our polar coordinate example here. So let's build up a data frame of polar coordinates. So let's build up maybe a circle of data. Maybe we'll have 100 data points. So if this were our polar data, we could calculate our Cartesian data by, of course, using our transformation that x is r times cosine of theta, and that would give us our x coordinate. And if we wanted to get our y coordinate, we could look at r times sine theta, just something like that. And if we were to plot this now in our Cartesian way, we get a nice perfect little circle of data. This is maybe a little too perfect and maybe not as interesting, so we could, for example, add some noise. Let's add some Gaussian noise, and let's put the standard deviation of that at 0.1 maybe. Pick your favorite value, something like that. That'll give us something that's not quite a perfect circle, but some kind of messy circle. And maybe we want to go a little bit smaller here. Let's go to 0.05. Let's just cut that standard deviation down. So it's pretty close to a circle, but it's not a perfect circle. And to make this a little more interesting, we could actually add in two circles. So let's call it maybe polar 0 and polar 1. In polar 1, maybe let's just change the radius to 5. And let's just bind these two together. So if we do this now, we're going to get 2 kind of concentric circles. Maybe 5 is too big. Should we do 2? There we go. We have 2 kind of concentric circles. And maybe we'll just bring up this variance a little bit here just to make it a little messy. Okay, so we have this data that is basically, we should be able to represent it kind of really simply. It's basically 2 groups, an inner circle and an outer circle, right? We just constructed some interesting data. And we could just do PCA on this. Let's say, let's not even use PR comp. Let's just say, let's X be our Cartesian data. What do you call it? Cart, right? So that's our Cartesian data. And then we can just get the SVD. If we just basically plot the U matrix of this SVD of X, this is basically, not exactly, but more or less what's going on if we do a principal components analysis on this thing. And you see that we don't actually get anything very different because it was 2-dimensional data to start off with, and so it's 2-dimensional data now also. And so PCA doesn't really do a nice dimensionality reduction on this. And it doesn't really capture what we can see by eye, which is that the data really consists of these concentric circles. And it'd be nice to capture that. And that's somewhere where something like kernel PCA should work out pretty well. So KPCA, let's say out is, we're going to run KPCA, we'll give it our data matrix X, we'll specify kernel, RBF dot was, so this stands for radial basis function, that is our Gaussian kernel. And we'll give it some parameters. Maybe we want the precision of this. So this is like inverse, like 1 over the standard deviation. It defines how tight our kernel is. And maybe we'll give it 0.2. Who knows? I don't know what the best answer here. This is unsupervised learning, so there's not really a best answer. And let's extract out 2 features like we did with PCA. We extracted out 2 features, basically give us back our original data set. Not too interesting, but if we run KPCA, we can extract out 2 features. We run it, and it's real quick. Now, this RBF dot, this Gaussian kernel function really is, implicitly it's embedding into an infinite dimensional space, so you'd think we'd have to be here for an infinite amount of time for it to compute, but our kernel trick allows us to do this without having to deal with actually embedding it in space, and so it's actually pretty quick. All I need to do is calculate that kernel function, which is plug it into the my Gaussian kernel pairwise for my points. Not too hard, and then do an eigendecomposition of it, and that gives us our answer. So we can plot our rotated data, for example. Boo. That's giving us something funky here. What's going on there? Not what I was expecting to get. Maybe if we adjust our sigma. So this seems to be giving us back our original data, which is a bit strange. What am I doing wrong here? Maybe if we make our groups a little more obvious here. Let's separate these things a bit more. Let's just bring down the noise. I feel like it's not using the right kernel. because it seems to be giving us back our original data. Strange. There we go. So it is sigma. So this is one of the, so let's go back. Let's leave this how it is. So here is our data with these two very obvious groups. It's an unsupervised technique, right? So we can't really cross-validate these things, but the sigma parameter is basically changing how my kernel is. So if I make it very small, it's a very flat kernel, it's going to give us something very similar to what we originally had. If I make it larger, it's going to give us something weird, but there's some kind of sweet spot in here where now we get this separating out nicely into two groups. So you can see here, basically, we have my two groups where I have my inner circle and my outer circle. And so this is separating. That first dimension here is basically the radius. So it's learned a non-linear dimension here. So we can go back, we could play with our data. I had, I think, 2 before here. And so the reason that we get this, which is kind of interesting, is it's going to depend on our sigma, and that's going to depend on the scale of our space. So you can kind of play around with these things. Maybe I'll put this at 1, so you can play around with different things. It's going to learn all these very complicated kind of non-linear functions of your data. So it's a very flexible method in something like a unsupervised technique. You have a lot of parameters and you're not in it, so it can be a bit difficult sometimes to figure out what's going on. And of course, you can play with other kind of kernels. So let's just adjust this. Let's add the data in, the noise in here. Let's just add in some uniform noise at the start. Between 0 and, I don't know, what do we want to do? 0.1? Sure. This way the noise structure will be a little nicer. Oh. Error? Why would it be giving me an error? Let's see. Let's just comment some spell. Let's see if we can find the error. That's not there. Well, that's not going to work. Let's try this. I think it might not like that. I'm missing a paren. There we go. Okay. So let's add the error in there. Okay, this is maybe a little easier to separate here. But you can see it can be a bit finicky. So that was original PCA. And if we run KPCA, sometimes it nicely separates it, sometimes it doesn't. So there's a lot of parameters here in an unsupervised analysis that can be kind of complicated. There's a lot of flexibility when you use when you use this RBF dot kernel, it's projecting up into kind of some infinite dimensional space. If you do it right, I mean, it's not really the right answer for unsupervised learning, but you can separate it into basically my first coordinate is kind of separating radius, more or less. And so that's really cute, where it's separating it out into my two groups, my inner circle and my outer circle. You can play with other kernels. Maybe we'll get interesting answers. Oh, sigma's not a parameter, so I can do polydot, which is polynomial kernel, degree maybe 2. And then I could say plot my KPCA. And maybe you'll get something interesting. Maybe we won't. So if I have a high enough degree here, presumably this is going to look so that's going to be complicated. If I use a degree of 1, that's going to be a linear kernel, and you're basically going to get back just normal PCA. I think you can actually even specify this as linear, right? Maybe it's called linear dot. Is that what it's called? Let's go back up to our help here. vanilla dot. It's the linear vanilla dot. Of course, it's called that. Okay. Should just give us our normal. Isn't that how you spell that? Should just give us our normal PCA. So you can see that kernel PCA is going to be a straight up generalization. Let's see if this. Oh, I know why. Because I have no argument to that. Got a space there. Still not happy. Not really sure why it's complaining. There we go. I guess you have to give it an empty list. That's a bit quirky. There are other packages to do this kind of KPCA. So this is the original one. You can obviously play with other kernels. The thing you see how much power you have by being able to push it up into this, embed up in this high dimensional space, and it can work out or it cannot. So it's a bit of a complicated method, but you see you can get. Now there's nothing stopping me, I guess, from looking at higher features. Here, I could plot like the second and third against each other, for example. What do we want to say? RBF dot. Isn't it called gamma? It's not called gamma. Sigma. It's called sigma. So it's a very these kernel tricks that give you a huge power, and sometimes it can work out well. You're able to pull out the structure, but you could see how if you don't hit it exactly right, you can not pull out the structure, and you can get things that aren't as informative. So these kernel tricks can be very powerful, but you have to be careful. So in an unsupervised technique like this, it can give you a lot of answers, and it's somehow times hard to know how to set the parameters. In a supervised technique, at least you can cross-validate for them, but you can't really do that for something that's unsupervised like principal components analysis. So that's a nice little introduction here to KPCA and kind of nonlinear extensions to PCA.